In MCQ 14, this is a shift away from electrolysis towards energy changes. So first thing, it was a reversible reaction. It's a little bit rare in O Level to have reversible reaction, right? Whereby they did mention that it's exothermic in the forward direction. Moving forward, it is exothermic. And that would have then meant that if I were to move backwards, the reaction would have been considered to be endothermic instead. Alright, just do a little bit of flipping. And as well as it being exothermic, it released the heat of 196 kilojoules per mole, so equals to 196 kilojoules per mole. We can either write it this way, or we can have written it as enthalpy change is equals to negative 196 kJ per mole. Now, the magnitude going backwards is actually going to be the same as 196 kJ per mole, or another way of writing is to go for enthalpy equals to positive 196 kJ per mole. Now, the activation energy of the forward reaction is given at a value of 75 kJ per mole. Now, this is the thing that we can't work backwards then, because the activation energy forward and reverse is actually quite different. So, key thing for this question here is that they wanted the reverse reaction. I highly encourage for us to draw the setup. Alright, so again, drawing out the first setup for the forward reaction. So labeling the axis is a luxury in MCQ. You don't really need to label, but since this is a presentation, we'll do it anyway. I'll have it as reaction pathway. And on the y-axis, I'll have it as energy with the units of kilojoules per mole. So just to give ourselves some things to work with, I'll just call this as reactant. I'll just call this as product. So the forward reaction is an exothermic reaction. In class, that would have then been mentioned that exothermic, we should be looking at the reactant to have a general higher amount of energy as compared towards the product. So linking them up, we'll be looking at two very important shortcuts that was again taught. The R to P direction of the arrows will be used to represent the arrows of enthalpy change, and the R to the peak of diagram will be used to represent activation energy. So this is reactant and this is product. So doing a general dotted line out here, you will see that R to P, this will represent my enthalpy change. And this will be equal to negative 196 kilojoules per mole. Now the peak of the diagram is found over here. So going from R towards peak, this will represent my activation energy value of 75 kJ per mole. Alright, so let's flip this equation the other way around to make it into the reversible reaction. So in the reversible reaction, the reactants becomes product and vice versa. So we're going to have the product to be much lower and the reactant to be much higher. So connecting them up, using a few things here, R as well as P. So this portion here should have been used to represent my enthalpy change. So you can see that it is actually not drawn to scale, but it must be the same. So this upward and downward, although the directions are different, the enthalpy values are going to be the same, except the symbol is going to be a plus 196 kJ per mole. Now activation energy on the other hand will be drawn towards the peak of the diagram. So from my reactant towards the peak of my diagram. Just draw this a little bit more accurately. This will be my activation energy, which is what I actually wanted to find. So just based off this portion here of the peak that's facing upwards, this should have been giving us a value of 75 already. But we need two portions here. So the bottom portion is also aligned with the yellow color portions of my enthalpy change. So to find out the activation energy in total, this will actually be 75. Again, the 75 came from the green area and coming from the yellow area of 196. This will sum up together to give us a value of 0.71 kilojoules per mole. So the answer for this question will be D.